Good afternoon. And welcome everybody. It is a pleasure. It is a pleasure today to welcome our speaker, Enrica Iodice. Enrica is a colleague and a friend from the Observatory of Naples in Capodimonte. Let me briefly introduce Enrica and summarize her working experience. Enrica got her PhD in astrophysics at the International School of Advanced Studies in Trieste, the SISSA, in Italy, with a dissertation with title Formation Scenarios of Polar Ring Galaxies, and the supervision of Magda Arnaboldi, Linda Sparkle, and Paolo Salucci. Then, after a few years as a postdoc, since 2004, Enrica is a staff astronomer at the INAF Observatory of Naples. And our guest is an expert in extragalactic astrophysics, particularly on observation and theoretical aspects of structure, formation, and evolution of galaxies in different environments based on imaging and spectroscopy. And today, Enrica will present the realm of low surface brightness features. So, Enrica, again, welcome. I give you the microphone. Oh, please
yes.
Show us with your presentation.
Yeah, thank you.
And I give you 5 minutes time.
Okay.
And
yes, I'm starting to share my screen.
And some.
Do you see my screen?
Okay.
The windows?
Yes, we see. Okay.
Okay.
Fine.
So,
okay. And we'll
enter.
Okay. So for the questions, we as usual we'll have them at the end of the seminar. So please, Enrica, go on.
Okay. So thank you very much, Michele, for inviting me and giving me the chance to talk about one of the project that I'm leading since 2016. I'm talking about the big survey with VST, and in particular today I'm going to show you the first results for one of the biggest target. This is the Hydra I cluster of galaxies, and I'm going to show the first results in particular range of surface brightness level that I named the realm of low surface brightness, since we are really looking at the galaxies in at a very deep level. Let me set the scene for this talk. We are interested in study the mass assembly of galaxies across several environments. I mean, from groups of galaxies to clusters of galaxies, and also voids. Why? Because we aim at constraining the formation scenario inside the lambda CDM framework. According to this scenario, simulation predict that the mass assembly is going on through the accretion of smallest structure to form the largest one. I mean, groups of galaxies merge to form the largest structure as a cluster of galaxies along the filament. In this process, galaxies undergone to several interaction, gravitational interaction and mergers. So there are features that generate from this kind of processes, and these are tidal tails, or the formation of the intra-cluster light, as well as the the accretion of the build-up of the outskirts of galaxies, the stellar halos, through the accretion of small satellites. So all these features I'm talking about are dominant. They are very faint, so they dominate at very low surface brightness levels, but they are the records of the mass assembly process. So we are really interested in this kind of structures and features. So to this aim, which are the observables, which are the quantities that we are going to measure directly on the images. These are the morphology of the galaxies. We derived the azimutally average light distribution, the colors and the colors gradients, the fraction of the intra-cluster light. Let me just stress for the non-expert that the intra-cluster light is a very diffuse and faint component made of stars and small stellar system like globular cluster, for example, that are not bounded to a single galaxies. But there is an unbound component that is present in the intra-cluster space between the galaxies. And finally, also the kinematics and metallicity are necessary to characterize such kind of features. The morphology is necessary to constrain the process of the mass assembly. I mean, just to detect how extended is a diffuse halo around the galaxies, to detect the low surface brightness features like the tidal phase or the shells in the galaxies. Mapping the low surface brightness in galaxies is absolutely important to constrain the different components in galaxies. I mean, the stellar component that formed originally in situ, and which fraction we have in the accreted component from this mass assembly process. The color gradients are necessary to provide a hint on the stellar population of the different components and of the different features. And the fraction of the intra-cluster light could provide a constraint of the look-back time of the assembly history. Why? Because theoretical prediction suggests that the amount of the intra-cluster light increases over the time. So in the local universe, we expect to find a higher amount of intra-cluster light with respect to high redshift clusters. And using the kinematics and stellar population and metallicity, we can constrain the structure and the stellar population of the different component. So to do this, which kind of data we need to study, to do this kind of study? We need multi-band imaging and also deep images and spectroscopy. We need a large covered area, and we also need a good arc-second level angular resolution. Why? To study the low surface brightness features, as I will show you in a while, we really need to long integration time because these features are really faint. The large covered area is necessary because mainly for nearby cluster, the stellar envelope and the intra-cluster light as well are really extended over several kiloparsecs. So we need to cover a large area around the galaxy and in the cluster. And the good resolution is, angular resolution is particularly important because we need to characterize fine features. which are not so much extended. So we need a good resolution. What about the necessity to have deep images? This is an example of simulated galaxy. This is a nice theoretical work from Silas and collaborators that show very well that the surface brightness level of a 29 magnitude per arc second square, which is already a really deep level for the imaging survey, the actual imaging survey. You can see very few details in the outskirts of the galaxy that they really show up in a deeper images, as you see on the left, of a level of 33 magnitude per second square in the deep band. So we really need to go as deep as we can to catch as much as possible details and integrated light in the outskirts of a galaxy. Sorry. And why large covered area? Because the stellar halos extends usually up to 100 kilopars from the galaxy center, but the intra-cluster light is even more extended, and this reach 100 to 200 kiloparsec from the center of the cluster. So, in the panorama of the deep imaging survey, we obtained the deep images from the VST Survey telescope, which is a medium class telescope, and the imagings, the multiband imaging survey that I'm going to talk about in a while are now acquired a pivotal role in the framework of a study about the low surface brightness features in the universe. Focus on the Vega survey or the VST survey of early-type galaxies. This is a deep multi-band imaging survey at the VST telescope. The VST survey telescope that you see here in the images is a 2.6 meters telescope located at Cerro Paraná in Chile. It is an enough facilities, but it's operated under an agreement between KISO and KINAF. The Vega survey is based on guaranteed time released at the INAF consortium that I'm leading since 2016. And at the end of the survey, it will be now in 2022 because we got an extension for the COVID pandemic that really stopped the operation for 6 months. We'll cover about 100 square degrees, and we will acquire about 50 targets as a cluster of galaxies and groups in a range of stellar mass of 10 to the 10 to 1014 solar masses. The 30% of the Vega survey was dedicated to the Fornax deep survey we did with VST that aimed to cover the Fornax cluster out to the virial radius of the cluster, covering about 26 square degrees. And this is a joint project between HINAF and the Omega Cam GTO led by René Pelletier in Groningen. The main signs that we released, both using both with Vegas and FDS, cover several aspects that I'm mentioned at the beginning. We were able to study the galaxy outskirts to constrain the intra-cluster light to detect and characterize the low surface brightness features. We were able to provide estimate on the amount of the accreted mass in the bright cluster members, just studying the low surface brightness profiles. Inside this project, Michele is leading the globular cluster science, and we obtained a beautiful two-dimensional image of the globular cluster inside the Fornax cluster, covering the entire area from the survey. And recently, we were also able to detect and study the ultra-diffuse galaxies in groups, in clusters. The Vega survey includes a collaboration mainly from enough institutes and some university in Naples and Padova, but there are also a lot of colleagues abroad that joined the Vegas team. One of the kickoff program of Vegas is the Ultra Vegas project. Since we just started the systematic search for ultra-diffuse galaxies in Vegas. The ultra-diffuse galaxies are extreme low surface brightness galaxies. They are very faint, have a mass similar to that of the Milky Way, but with a stellar mass 100 smaller. Typically, they have a central surface brightness lower than 24 magnitude per second square in the D-band, and an effective radius larger than 1.5 kiloparsec. The nature of these objects it's still not clear, and the observations available for the UDGs do not fit in a single formation scenario. There is an hypothesis that they could be failed galaxies that where the gas reservoir was stripped away, and they just quenched with respect to the normal evolution of a galaxies, or they are an extreme class of dwarf galaxies. I mean, they just formed in the same way, but for some other kind of processes, they are so diffuse. Also, the content of dark matter in these galaxies is not clear yet, because there are some objects that seems to show a very low amount of dark matter content, and this suggests strongly suggests to as a strong indication to revise the entire formation theory about the galaxies. This plot shows the Van der Waals relation about the number of globular clusters as a function of the halo mass in the environment. I mean, groups or clusters. And these are the points that are already on this relation, where the already detected UDGs in several clusters of galaxies, and the number of UDG increases with the halo mass of the environment. So in Vegas, we aim at in this range from 10 to the 12 to 20 to 14 halo mass. We aim to systematically search for ultra-diffuse galaxies, and we should be able to detect 1,300 new objects, and we are able to fill more the gap at the low mass in the low mass range in this relation. So we could provide we could provide a new catalog that will turn to be also could have a legacy value for future follow-up imaging and spectroscopy follow-up. These are the first detected ultra-diffuse galaxies in one of the group from the VST images published in 2019 from one of the Vegas COI, and this is a set of new 9 UDGs in another group of galaxy, EC 1459, also based on the Vegas survey published more than 1 year ago. And interesting, you see here that the detected number of UDG in this group is in the number halo mass relation is just what we expect for the halo mass for a group of with this halo mass. So this could be considered, could suggest that the images, the data that we have, have the necessary depth and resolution to perform this kind of studies. The first detection of a sample of ultra-diffuse galaxies in the Hydra I cluster was published 1 year ago. The Hydra I cluster is a rich cluster of galaxies at about 50 megaparsec from here. This is the VST mosaic that we obtained. It's 1 times 2 square degree. And these are listed in this table a few important properties of the Hydra cluster. In particular, you see the dynamical mass. There is a large emission of X-ray. This is the entire catalog of dwarf galaxies already available for this cluster of galaxy, and we mapped with the VST images almost the 0.6 virial radius of the cluster. These are the new low surface brightness galaxies that we detected just by visual inspection in this cluster. At that time, we published the first catalog that includes the first 12 UDG is cluster. Looking at the color magnitude relation, that it's an instrument for us to see if they are reasonable cluster members. And as you can see, all the new low surface brightness galaxies, in particular the UDG, are reasonably cluster members. Here I show quickly some images just to give you an idea of which kind of galaxies we are studying. There are all the new UDG in Hydra, and in the space of parameters just to define the UDG, you see that they are fainter than 24 as the central surface brightness, and larger than 1.5 kiloparsec. For some of them, for the entire sample, we studied we detected the globular cluster. And why this is important? Because the number of the globular cluster in the UDG could provide, through the relation published recently also by Burkett and Forbes, an estimate of the total halo mass of the UDG. So we have compared these values derived for the UDG in Hydra, with other observation for UDG in coma and for the, let's say, normal dwarf galaxy. The normal dwarf galaxy has, on average, a specific frequency of the globular cluster that is lower than typical value of specific frequency for the UDG in the coma cluster. In Hydra, we still see an excess of globular cluster in the UDG. We are, let's say, at the upper limit of the values derived for the dwarf galaxy. And then, as I told you before, in the coma cluster, UDG have a larger specific frequency than dwarf. What about the halo mass? I mean, the dark matter content. This is one of the more delicate point. This is the average relation for normal galaxies. And the black points are the estimates for the coma UDG, and the red points are for UDG we studied in Hydra. And you can see here we cannot say nothing more than it seems that values are similar to the dwarf galaxies or comparable mass for the UDG in Hydra. On the other hand, as we already know, the UDG in coma have a higher halo mass, so they seem to be dark matter dominated. We have improved the search of the detection of the UDG in Hydra cluster by applying an automatic detecting tool, I mean structure. And this is the topic of a master thesis of my student here in Naples, Antonio Lamarca, and he derived a new sample of dwarf galaxies in Hydra. They are in total 219 new candidates, and 20 of these new low surface brightness galaxies are ultra-diffuse galaxies. They are in this located in the space of parameters, its characteristics for UDG, and all of them are reasonably cluster members. If you will look again at the number halo mass relation, you see that this is a total number of 30 ultra-diffuse galaxies inside the 0.6 virial radius. Is just what we expected according to this relation. Producing, just based on the total number of new candidates and including also the previous catalog about galaxies in Hydra, we derived the two-dimensional distribution of galaxies that I'm going to show in this plot. And what you can realize soon is that Hydra is made of several substructures. You see several peaks in the density. One is the core, and then we at least two groups, one in the north and one in the south, plus few other subgroups. This suggests that Hydra is in an active phase of assembly. And now I just going to show to analyze each of these groups in detail. I mean, what we can see from the deep images from Vegas. So start with the core. The core is dominated by the two brightest cluster members, 1311 and NGC 1309, that I labeled on this image. They are embedded in a very large diffuse halo, as you can see around them. but there are a lot of bright galaxy members around. All these, all the system that I have labeled here are cluster members close to the core. Hydra was well studied in the past, both from images, but also using the spectroscopy. And the main result suggests that the extended envelope around the two bright cluster members is off-center with respect to them. And there is also a kinematic different component with respect to the main galaxy. It is there are a lot of fine structure, and there were already detected some debris that could be reasonably the remnant of disrupted dwarf galaxies in halo. So we expect that the mass assembly there is really going on. And if you look at the black contours are the X-ray emission, that it's also asymmetric with respect to the center of the cluster, where you see an overdensity. It's elongated toward northeast, where also the envelope show an extended structure here. These are the surface brightness, the azimutally average surface brightness profiles that we derived for the two galaxies per panel for 1311 and the local panel for 1309, where you see that we reach on average a surface brightness level of 28 magnitude per arc second square. This is really extended around 200 kiloparsec. I mean, we are 0.14 of the period radius. And this is the region, this is the distribution of the stellar envelope around both galaxies. And the light, the total light in the stellar envelope is around 3 times 10 to the 11 solar luminosity. This means that the stellar envelopes around the two galaxies contribute to around 60% of the total luminosity of the galaxies. And recently, based on the news data, Barbosa and collaborators suggested that the envelope is really a distinct kinematical component with respect to the central galaxies. If we subtract the light distribution from the two galaxies, here you can see some residual features. What I have marked here were already discovered from previous Wi-Fi data that just covered the core of the cluster, and both of them were explained as the disrupted dwarf galaxies. But there are a lot of low surface brightness features around several galaxies into the core of the cluster that were not known before, just because they were not available large-scale imaging data as we have now. And here you can see some of them I have highlighted with these dashed lines. You see S-shaped tail or extended halos around 3308. And in addition, if we subtract all the brightest galaxies around in the core, you see that some extra light remains here, and this is a patch of intra-cluster light that contributes to the total light of about 10 to 7 solar luminosity. This is in the core. If we move north, there is this group of galaxies that it's extended north-south with respect to the core. All the white arrows indicates the brightest galaxies in this core, which also show a lot of faint features, like the shells around HCC 020, or these really strange comet-like galaxy, HCC 005. In this case, I was convinced that this is two features are superimposed. They are one over another. I mean, galaxies, and there is something, and there is something close in projection to the galaxy, because the isophot of the galaxies are not so much disturbed to explain such a huge extended thick tails. In the southwest part of the galaxy, there is another already studied low surface brightness object that is HEC 087. This is using force data. This was a study, and it turns to be a tidal disrupted dwarf in the potential of the cluster. And more in the north, there is a lot of light, diffuse light in this region. And if we account for the brightest galaxy and we subtract the light from the brightest stars, the contribution of the diffuse light in this region is around 10 to the 10 solar luminosity, and the average color is about 0.6 magnitude in G minus R. And if you look at this strange low surface brightness feature here, I don't know what it is yet. I don't know if this is the remnant of a destructive galaxy. For sure, it's really large. It's about 29 kiloparsec. Has a similar colors to the diffuse light, and it's very faint. It's about 27 magnitude per second square, and there's a total luminosity of around 10 to the 8 solar luminosity. If we move to the southwest region, the other peak in the density of the cluster, this is a completely different environment. These are the brightest galaxies of the group. Most of them Lie-type galaxies, so spiral or a zero, and barred. And to best of my knowledge, there is no detectable intra-cluster light, but there are strong signs of environmental effect. Have a look. This is the giant spiral galaxies, NGC 3312, that show extended stellar filaments here in southwest, and a distorted morphology in the outer disk. If you look here, the surface brightness images show better this kind of features, and I have also marked them. We are here with the dashed lines. Other really interesting object is the couple of galaxy NGC 3314A and B, because these are two galaxies close in projection. One is in front, that is 3315A, and the other one is behind, the 1314B. These galaxies were already show for the VST images, show for the first time a new extended stellar filaments in the southwest direction. they extend for roughly 50 kiloparsec. This system was already known by HST images, but except for this overdensity of light here in the southwest, the long stellar filaments were not yet detected. What is still unclear, if this galaxy is a jellyfish galaxy, I mean, if this this tail of stellar filaments is just the results of the round pressure stripping, I mean, the gas in the disk was expelled from the disk during the interaction of the galaxies with the hot intra-cluster medium in the core, and so the gas clumps reach the right density to form the new stars. Or if this is the result of tidal interaction, and so this is a tidal tail. There are previous Holder study about the H1 from McMahon and collaborators of 1992 that suggested that this galaxy and the other giant spiral galaxies, 3312, probably are part of a foreground in falling group in the cluster that went through gravitational interaction. And finally, there is this galaxy as part of the group. Here I show you an example of one of the largest UDG in the sample that I show you before the new detection, just to give you an idea of this kind of object. But what is interesting in this galaxy, NGC 3016, is several stellar streams in the outskirts, and I analyzed them in detail. If you look at the isotopes, you see that they are really boxy in the outskirts, and this is a sign of a known sign of interaction, or better, of an accretion of a minor satellites from the galaxy in its outskirts. So subtracting the light from the galaxy, these stellar streams and the bright node here stand out very well. And I checked if they have similar colors to the average colors for the dwarf galaxies, because our idea is that this stream is just the disruption of a dwarf galaxy in the halo of this galaxy. And the consistency between the colors is a point in favor of this idea. So, just some conclusive remarks on this ongoing study. There is still work to do, but probably I hope to publish all this stuff in one large paper during this year. Anyway, taking advantage of the large field of view of omega m, which is 1 square degree, the long integration time, and also an ad hoc observing strategies, we were able to explore to the low surface brightness regime for this cluster to detect a new feature out to 0.6 period radius of the cluster. We detected the new dwarf galaxies and ultra-diffuse galaxies that are going to be also published and studied in detail. And all this, all of them indicates that the Hydra I cluster appears to be really in an active phase of assembly. So we are just catching in act all this assembly phase where subgroups of in the large scale structure are merging to form the entire cluster of a galaxy. And to finish, we are able to derive an estimate of the intra-cluster, the total intra-cluster light fraction in Hydra. Here there are points accounts for already known estimate for intra-cluster light in cluster of galaxies of comparable mass. I mean, the Fornax cluster, the Coma, and the Virgo, which is in an early phase of evolution. So there is less intra-cluster light there. Compared with the theoretical prediction from continued collaborators of 2014, and Hydra this year, we detected roughly 20% of the intra-cluster light in Hydra, which is considering the errors, the uncertainties on these values, fully consistent not only with the other estimate, but also with the theoretical prediction. This is just let's say, I'm going to show you these first results, but it is an ongoing work, and so more thought are needed. So I can stop here.
Okay, thank you. Thank you.